So, good afternoon to everybody, and welcome to the fifth Eurados webinar with the title of Dosimetry for Workplace and Environmental Radiation Monitoring. So, I am Arturo Vargas, researcher of the Technical University of Catalonia in Barcelona, Spain, and I am the Working Group 3 of Environmental Dosimetry Chair of Eurados. Starting, I will give you a very brief overview of Eurados. You can see here that we have almost 600 active scientists contributing to Eurados objective. As you see, Eurados is divided in 8 working groups, and you see the environmental dosimetry working group, which, as I say, I chair it. As the main activities of Eurados is the coordination of working groups. These working groups promote technical developments and its implementation in routine group work. Also contributes to harmonization within Europe and obviously performs scientific research. It's also very important the organization of intercomparison and benchmark studies, and the organization of scientific meetings and conferences, training activities, winter schools, and so on. We make an organization of annual meetings with more than 300 participants. And if we go a little bit more in detail on the topic of today, which is inside this Working Group 3. Working Group 3 is divided in 3 subgroups. The first one is devoted to the spectrometry system for environmental dosimetry. Is more related to early warning networks. It was created in 2012. Before, obviously, there were other activities, the same activities, but in one group. And there is different working packages. And I will only to point out that here, working package 4, it is proposed also a webinar for September regarding airborne spectrometry detectors for unmanned aerial vehicles. Then we have the subgroup 2, which is the passive environmental dosimetry. Is Christian Kraniski was the chair, and now is Stefan Neumayer from PTV. And this is the subgroup that are regarding this webinar, and has 2 main tasks. One is the current status of the passive dosimetry system used in European countries, is the questionnaire we will see today, and also the organization of comparison that you also will see today in the webinar. Finally is the subgroup 3, which is the newest group, and is regarding radon, and it's Annette Rödger from PTV also is the chair of this subgroup. Regarding the questionnaires, there has been carried out questionnaires since 2013, and there were about 20 questions in the questionnaire regarding different topics, and this questionnaires has been analyzed, it has been compared, and with the results that has been reported, has been elaborated a Eurados report, which this is overview of passive area dosimetry system used in European countries. So for this reason, we have prepared this webinar, or one of part of this webinar, and Maria Morduk, my colleague from the university, will give you this talk about the passive area dosimetry system used in European countries. Furthermore, Working Group 3 subgroup 2, they carry out intercomparison, which is very important for Eurados and this our group. Here I will point out some history of comparisons, what we call area comparisons of dosimetry. We install in an area, which you can see in the picture, and we make comparisons. The first 2 ones, it was more organized by PTV, and participation was about around 14 systems in one of them and 20 systems in the other one, 2005, 2011, 12. Then it comes the first Eurados comparisons. It was about 6 months, and it takes from May 2014 to October 2014. It's called ICN 2014. And you see the increase also in the systems participants there that was in this first Eurados comparison. It was also a paper on that you can see here on radiation measurement journal. Then there was another comparison that it was really involved this subgroup of Eurados, and it was done in the framework of the European project preparedness. It's a Euramet project. And also you can see the increase of the number of systems here, 38 systems there. And in this comparison, you can see that it has been used, the PTV facilities, for determination of the cosmic radiation. That you can see the lake there. We use the lake, which is the inner background on the cosmic. Then we have the Euro 2 with underground lab, where almost no radiation are there, so you can measure the inherent of the detectors there, the inner background. Then we have the lab irradiation, and also this area where we measure cosmic and terrestrial radiation. It's also a publication on this intercomparison. So now there is ongoing another comparison in this topic, which is called IC 2021 area, and the registration has just ended in 31st May, and I have to say that there are excellent preliminary status. It's increasing again the number of registered dosimeters there now is 58, and there are participants from different institutes, countries, and even non-European countries like Argentina, Canada, Japan, and Morocco participated on that. Also, almost half of the institutes are stated to be Eurados sponsors. Furthermore, we have another kind of comparison, which are called comparison of calibration methods, and it's IC XXX means the year, and it's count from calibration methods. Basic methodology is that every laboratory irradiates this kit dosimeter in their facility, and it's compared with the results of the reference lab, which these dosimeters are also irradiated in the PTV. So 10 dosimeters are irradiated at PTV lab, and each lab irradiates the dosimeters with 5 dosimeters are irradiated, and the other 5 are for transport. You can see here the results of the 2 campaigns that has been carried out in 2017 and 2018 with 15 and 14 participants there. And now, or just finished the last one, that it was the IC 2020 count comparison that has been managed by Christian Naber, and he is going to show you the results of this last comparison campaign on the title of results of last comparison organized by Eurados IC CALM. So I think that's all that I would like to say. Just enjoy the webinar, and please do not forget to write your question in the chat, and the moderators, they will ask them at the end to the speakers, yes, of both presentations. So thank you very much, and I give the floor to Maria Moore in order to give your first talk.
Okay, thank you, Arturo, for the nice presentation. First of all, let me say hi. Good afternoon to everyone. As Arturo has said, my name is Maria Amorduc. I am a researcher of the Universitat Politécnica of Catalunya, and I'm going to talk about passive area dosimetry systems used in European countries. But anyway, just let me say a few words about how we gathered all this information. Arturo has said something, but I think it's interesting to see how we gathered all the information and the process to analyze and compile all this information. So, as my first slide, let me go back to 2012. And at that moment, in Working Group 3 of Eurados, it was discussed that as regards passive dosimetry systems, could be interesting to identify needs and requirements, open questions and problems, and of course, new developments and topics regarding passive dosimetry. especially applied to environmental dosimetry. This information was planned to help to assess the possibility of planning of an international intercomparison of basic dosimetry systems, but also the possible implementation of a specific subgroup of basic dosimetry within Working Group 3. So the first task was to set up a survey to gain an overview of basic dosimetry systems and procedures on how doses are being calculated in these services. So within the group, it was prepared a first questionnaire with 20 questions, and the main core of this questionnaire was devoted to the basic characteristics of the dosimetry systems. So we have 6 different questions regarding basic characteristics, but also, of course, additional questions devoted to those calculations methods, also some questions about quality assurance, and also about customers and interest in intercomparisons, and to set up a new subgroup in Working Group 3. So the first questionnaire, as Arturo said, was disseminated by email in 2012. So here, the ideas that we collected during 2 years, so up to 2014, we collected different questionnaires during these 2 years, and we analyzed the results. I've made a selection of the main results, but of course there is a lot of information that we gathered with these questionnaires. But as I've said, I'm going just to show you the most important results, or that I think that could be of interest for the audience. So first of all, the first result was how many questionnaires we gathered. The idea is that by the end of 2014, 60 questionnaires were received from 47 different institutions and 24 different countries. It means that there are some institutions that use different dosimetry systems. This is why we had more questionnaires than institutions, because some of them use different detectors to evaluate doses in different conditions. Also, you can see in the graph on the left and the bottom of this slide that we get results from different countries, but of course there were some countries that especially participated in this survey, and we can highlight, in my case, is Spain, because I was in charge to try to disseminate the questionnaire, but also a lot of services from Germany and also from Belgium and Italy. Okay, so the idea is that we think that we get a very good representation of dosimetry systems in European countries, because of course we didn't have an answer from all the European countries, but we have at least 21 countries from the 28 of the European Union countries. So we believe that it is a very good representation of this situation. So I'm going to show you different results regarding different aspects of the questionnaire. And now at the beginning, as you can see here, I'm going to show you some results about the questions about the dosimetry system. As I've mentioned, these questions were focused to get a basic characteristics of the dosimetry system. So we asked about the measuring quantity, the radiation detected, the basic dosimeter properties, how many dosimeters are used per measuring period, the weighted ranges, and other questions that we thought that were of interest at that moment. So as a first result, let me say that what we could observe is that the size of the service was quite different among them. Most of them were small, but instead, in reality, very small services. Small, it means more or less than 100 dosimeters issued per measuring period, but in many times we observed a lot of services that just sent around 10 or less than 10 dosimeters per measuring period. But at the other side, on the contrary, we had very large services that issue more than 2,000, 3,000, 4,000 dosimeters per measuring period. So this is we have to do a balance between these differences among services. The next result that we get was about, as I've said, which is the operational quantity of use. And as you can see here, in most cases, they say that they use Hstar 10, the ambient equivalent dose. But there are still, at that moment, there were still some services that indicated that they use HP 10, which is not the right operational quantity of use in area dosimetry. But at least they indicated that they were aware that this was not the right operational quantity, and that the client was, the customer was aware about this situation. As regards the radiation detected by these passive dosimetry systems, as you can see, in the majority of cases, we are talking about photon dosimeters, and a very few systems were neutron dosimeters, and even less, they have the possibility to measure photons and neutrons. So what I'm going to show you, of course, is mainly related to photon dosimeters, because we gather very few information about neutron dosimeters because they are not really used too much. As regards which is the sensible element of the dosimeter, as you can see in this chart, thermoluminescent detectors are the most widely used passive detectors. The TLDs with 83% of cases. But of course, there are a fraction that use optically stimulated luminescent dosimetry, or RPL, or direct ion storage, or CR39, or fission track. But as you can see, the vast majority of systems use thermoluminescent detectors. Among thermoluminescent detectors, we can also say that lithium fluoride with magnesium and titanium is still the most commonly used TL material. Among these systems that use thermoluminescent detectors, 40% of the dosimetry services use this lithium fluoride, magnesium, and titanium. But it was closely followed by lithium fluoride with magnesium, copper, and phosphor in 34 of cases. So it means that these ultra-sensitive materials, such as lithium fluoride, magnesium, copper, and phosphor, are still growing up. Maybe just to compare with previous data, let me say that we had some previous results from the last large-scale international intercomparison organized by the Environmental Measurements Laboratory of the USA. And in that case, in 1999, calcium fluoride was the most commonly used material. And this large-scale international intercomparison, there were in this intercomparison, there were 150 participants. So it's quite a change. Now we move to lithium fluoride, magnesium, titanium, and it seems that we are moving on, still we are running to lithium fluoride with magnesium, copper, and phosphorus. What else we can say is that how many dosimeters are used per issuing period, or in this case, what I'm going to present you is the different issuing periods of monitoring periods that are used by the different dosimetry services. As you can see, we can see very different measuring periods from 1 month to 1 year, but the most common or the most frequently used monitoring period is 3 months, which means that we issue dosimeters in a quarterly base process. What else can I highlight about our results? For instance, the rated ranges. I think it is important or nice to see the rated ranges. As regards the dose range that the dosimetry service has indicated, you can see that we have a very different situation as regards the lower dose range limit. We have a minimum stated value of 1 microsievert, and on the opposite situation, up to 200 microsieverts of this lower dose range limit. As you can see, or you can imagine, the idea is that the distribution of the answers does not follow an unimodal distribution. And in fact, it's not right to use an average, but just to give you an idea of which could be this average, is around 54 microsieverts for the lower dose range limit. As regards the energy range, as you can see, the dosimetry services indicated a minimum stated value in some cases of very, very low energy of 5 kiloelectronvolts, very, very low for an ambient dosimeter, and a maximum stated value for the lower energy range limit of 100 kiloelectronvolts. Once again, it's not a nice distribution, so I present you this average, but it's not really a nicely distributed distribution. So, but just to have an indication, you can see that the average of this lower energy range limit was about 29 kiloelectronvolts. What else about basic characteristics? I think that's all. So now I'm going to show you the results, or some results, regarding the questions about the methodologies to calculate doses. At this moment, I think it's worth remembering how is the usual process of the use of a passive detector to be used for dose monitoring. As you can see, the first stage is to prepare the dosimeters. In most cases, it means to anneal the dosimeters. In some cases, also to irradiate a fraction of the dosimeters to a reference dose, and of course, the packing and prepare the dosimeters. Then the dosimeters are sent to the monitored site, and they are exposed at the monitored site. At this situation, the detectors are exposed, of course, to natural terrestrial radiation, to secondary cosmic radiation, and the most important part is the one that we are looking to monitor, is the possible excess radiation due to artificial radiation. After the measuring period is finished, the dosimeters are returned back to the dosimetry service, and then the readout is carried out, and then those calculation methodologies could be different to get the final dose. So with this in mind, this is why we set different questions regarding this situation. We have, when we prepare these passive dosimeters, as they are integrating dosimeters, once we put to zero the detector, they start to integrate. So we have an inherent background during the handling and the package. We have this transport dose when the dosimeters are sent to the monitor's site and go back, the corresponding doses at the monitoring site, and all of this makes a whole, which is the measured dose. So our questions were about if a net dose calculation is applied, if any transport dose correction is applied, and which is the methodology to do these corrections. If in the case of thermoluminescent detectors, as they can show a fading effect or a climate effect due to an intentional loss of signal, which could be variable depending on the TL material. So we asked about if the methodology contemplates this fading correction or not, if there were other applied corrections, and the last point, and not least, whether the overall measurement uncertainty is calculated and reported or not. So now the results. As you can see, here you have the 5 questions, the main questions about those calculation methods. And as you can see, only 30% of the services subtract the natural background from the dosimeter results. So it means that we are, in most cases, providing just a gross dose. As regards the transport correction, half of the dosimetry services apply transport dose corrections. And regarding these fading corrections, I just highlight once again that this is the unintentional loss of signal of a thermoluminescent detector. Around 43% of services apply a fading correction. So, as I've mentioned, it depends on the material. So for some dosimetry services, this correction could be important, but for other ones, it is not necessary to apply these corrections. As regards other corrections, the services that apply other corrections are mainly related to individual calibration factors for each TL or each detector. And finally, regarding the calculation of the overall uncertainty, I think it is quite interesting to see that most of the systems calculate the overall uncertainty. So it's quite nice to see that we didn't ask about which was the value, but at least at that moment, we knew that most of the services have this value calculated. Another main group of questions was about the quality assurance of the results, and we mainly asked about the participation in other intercomparisons, the traceability to national or international standards, and compatibility with the international standards such as the IEC 62387 or IEC 17025. And the results about these questions, here you are. As you can see, most of the services participated in past intercomparisons, so they would probably would be interested in participating in next intercomparisons. As regards the traceability of the systems, we get some surprising answers because we expected that everyone indicated that it was traceable, but some of the systems indicated that they were not traceable, and maybe this was just a confusion of the terminology, because maybe they say just that we are not directly traceable, but of course, probably all of them were really traceable. As regards the compatibility with specific standards, regarding the validation of these standards and its characteristics, as you can see, not many dosimetry services at that moment were compliant with IEC 62387, but they say that they were compatible with other standards, old IECs or some German standards. And the last one, also interesting, is that most of them were accredited according to ISO 17025, which means that they have a quality system implemented in their systems. And as I've mentioned, we have some questions about customers and further interest. And one important result from the survey was that 100% of the participants expressed their interest to take part in an international intercomparison within this field. And as Arturo has mentioned at the beginning, according to the results, in 2014, Eurados organized the first Eurados intercomparison of passive area dosimeters. And here you have the corresponding information of the paper we published regarding this issue. So, as you can see, a lot of results. These are not all the results, but at the end, we're analyzing all the results. We identified that there were some open questions. We didn't have the whole picture that we needed. So, for instance, many services indicated that they used several different materials within the same dosimeter, but in that case, they didn't indicate which was the TL material. Or, for instance, we get the knowledge that they calculated an overall uncertainty, but maybe could be interesting to know which is the value. We identified some issues about traceability and calibration procedures. And of course, we also were interested in further interest of the dosimetry services. And this is why in 2016, so a bit forward in time, we prepared a second questionnaire that was distributed, and we collected questionnaires until 2017. We have some specific goals just to complete the information we get from the first questionnaire. So our specific goals were devoted to just to get this information that we identified we needed, but we kept some of the questions the same because we wanted to be able to compare the old data and new data. Because if most of these answers were quite similar, we can just say, okay, the picture is still the same, and now we have this new information. And this is what happened. More or less, we had, for the same questions that we had in 2012 and 2016, the whole picture was quite similar, but of course we get more specific information. Just to have an idea, in this case, this second questionnaire, we didn't have so many answers as at the beginning, but we get 29 answers from 24 different institutions and 12 different countries. And the next slide is just to show you this added information to the previous questionnaire. For instance, about the TL materials, in the specific case when a mix of materials within the same dosimeter is used. As you can see, in 2012, we have a lot of responses that just say it's a mix with more details. But now, with the second questionnaire, we can see that when there is a mix, the most commonly used is a mix of lithium fluoride with magnesium, copper, and phosphorus, plus lithium fluoride with magnesium and titanium. Please, maybe it is worth remembering that when we use different TL materials within the same dosimeter, is because we try to do a better energy response of the system, or maybe sometimes the users, the services, they use different isotopic compositions of the same material, for instance, lithium, just to get a different response against neutrons than from photons. But as you can see, now we have more results. The picture is quite similar, but at least we have more specific results. We had a specific question, not also about the rated ranges, but a specific question about the lower limit of detection of the dosimetry services. And as you can see, once again, this is not an unimodal distribution at all. And you can see a lot of systems that stated that the lower limit of detection is below 5 microsieverts, but also we had the opposite situation, systems with more than 100 microsieverts of lower limit of detection. So the characteristics of the systems could be quite different. As regards the overall uncertainty of the dosimetry systems, here you can see the picture. We have this a minimum value around 1-2% of the overall uncertainty, and the highest value around 30% of this overall uncertainty. And as you can imagine, for us, it was a bit surprising to get some values very, very low, between 2-5%, because in most cases, the calibration, it means an uncertainty of this level. So this indicated that maybe it could be worth investigate and harmonize which are the methodologies to calculate these uncertainties. We had also a specific question about which were the contributions taken into account to calculate this overall uncertainty. And as you can see, in most of the cases, the services applied the typical contributions to the overall uncertainty, which is the statistical variation, the calibration, the uncertainty coming from the calibration, from any possible non-linearity of the response of the detector, of course, the energy and angular response, and so on. So just I'm going to finalize quite fast because I'm running out of time. But as you can see, when we talk about the calibration, cesium sources are the most commonly used sources, and the most frequent situation is to calibrate the systems once per year. And also an interesting situation was to ask the main causes of error when assessing a dose with a passive dosimeter. It was not a surprise that the biggest problem is to have lost or unreturned dosimeters or a damaged dosimeter. So, because then we lose all the information. And the last one is just, we ask about the interest in future intercomparisons, just asking to specify specific items. And as you can see, the most voted situation was an intercomparison devoted to low doses. And this is why the current intercomparison is focusing in this area. So to finalize, let me say that I think it's more or less evident, the quality of the calibration method has a direct influence on the accuracy of the measured results, and this is why we started the intercomparison on calibration procedures. A discussion on the uncertainty contributions and the methodology to calculate the uncertainties would be very helpful, and of course there is still a need for harmonization in this field. So this was just an overview. You can get more details in all the related articles and publications. And last but not least, let me say that all this work has been done with the collaboration of many researchers of different institutions, because Eurados has a collaborative spirit, and this is why I put this picture from a sardana. Sardana is a typical dance of Catalonia, where we dance all together. Everyone can join the circle and help. So your contributions, if any, from the audience are always welcome. But let me just, I want to thank especially, I'm very grateful to Harald Dombrowski, to Christian Hranitsky, and also to Maria Ranogayen-Komor, because they really supported all this work, and they have a very high commitment. And now I hope that all of you are still awake. If not, I'm trying to see if you are awake or not. I'm going to ask to the audience some questions, very short questions, just to know who you are and maybe to identify some possible interest for the future. So we will open two polls, two very short questions. So as you can see, the first one is to know if you are involved in a dosimetry service. I think I can vote, so I'm going to say yes and send the answer. We are going to let these polls open 1 minute or two. And as you are going to see, there will be a second poll, because as you can see, we identified that could be a need for more harmonization in this field. And we wanted to ask you if you will find interesting to promote a document or maybe a standard with recommendations for area passive dosimetry. So if you are interested in promoting this kind of document, just say yes. And if it is not the case, just say no. Okay. So once we gather these results, I'm just looking at the results, and for the first question, let me say that half of the audience are involved in a dosimetry service, around 53%, and the other ones no. So for me, it's nice to see that people who are not involved in a dosimetry service is also interested in this kind of webinar. And to the second one, I'm very happy to see that, let me see, around 90% of the audience think that could be interesting to prepare or to work on this kind of document or recommendations on this field. So just let me say that thank you for your attention. As Arturo has told you at the beginning, all the questions will be answered at the end of the webinar. In fact, I'm going to start to compile of the questions, and then we will prepare the answers. Now I'm going to give the floor to Christian, who is ready for the presentation. I'm sorry for being a bit late, Christian, but no now problem. The floor is yours.
Okay, thank you. Yeah, also from my side, good afternoon, ladies and gentlemen. Last, as well as least, my little presentation about the IC 2020 CALM. Arturo already told you about the intercomparisons, some things. First of all, the goals of the task, what was the idea behind this kind of intercomparisons? We want to provide an international performance test of the calibration capabilities of different institutes all over Europe, plus the rest of the world, performing internal or customer calibrations. We issued certificates for all of them to show to their authorities or the auditors during an accreditation or whatever. It is planned to have a publication of all the intercomparison results and the technical recommendations. And of course, one big goal was to discuss and optimize all the calibration procedures and the uncertainties. Okay. You also saw it in Arturo's presentation. We already had two intercomparisons in the past, one in 2017, which was only in the framework of our working group at Urados, just to test how everything works and if the stuff, how we planned it, turns out to be fine. And then the year afterwards, 2018, we had a second intercomparison, which was more or less the same boundaries. The dose we demanded was a little higher, and the first one was 3 millisieverts, and the second one was 10 millisieverts. And we thought, okay, we have to go on because the reactions of all the people we talked to were very positive. But the thing was, we wanted to go one step farther, to give a few more options. So Christian Waninsky of the Cyberstorf laboratory, he provided a small expression of interest, which we sent to the, let's say, usual suspects of the working group 3 in October 2019. And there were basically two questions. The first one was, how about the dose meter type people want to irradiate? Only passive area dosimeters, or only passive personal dosimeters, or even both types? And you see most of the people who answered the poll wanted to irradiate both types. And the second question was, how about the radiation quality? Still only cesium-137 or only N60 X-rays? And also, in this case, most of the people wanted to irradiate both qualities or only cesium. So what happened was we had 4 categories, which is first one, Hstar 10 area dosimeters irradiated with cesium-137 gammas, Hstar 10 area dosimeters with N60 X-rays. The dosimeters were provided by us, by KIT. Oh, I'm Christian Alva from KIT Germany, by the way. 7 pieces per participant plus and category, plus 5 for the background. And then we had HP10 person dosimeters, cesium-137 gamma, as well as HP10 person dosimeters irradiated with X-rays. And they were provided by the Auswertungsstelle in Munich. In this case, 8 pieces per participant and also 5 background dosimeters. And for all the participants, it was possible to choose only 1 or 2 or any 4 of the categories, as well as all of the different connections. Okay. So what were the calibration conditions? We had cesium, as I already mentioned, 137 photon field and or N60 X-ray radiation field. We decided to stay with the 10 millisieverts in terms of Hstar 10 and or if the people irradiated person dosimeters HP 10. The dose rate and the irradiation time was arbitrary, as well as the distance to the source, the field size, of course, preferably a homogeneous field was to be chosen, as well as the use of a PMMA build-up plate was also left arbitrary by us. So for the positioning of the dosimeter, concerning the reference point and the orientation, we provided illustrations and we preferred single dosimeter irradiations. The two types of dosimeters, as I already mentioned, was the KIT Hstar 10 sphere. You can see here, it's an isotropic sphere made of PMMA with two TL detectors in the middle of the sphere. So the reference point, as you can see on this photo, is in the center of the isotropic sphere. And the second dosimeter was the personal HP10 dosimeter, which is provided by the Ausleitungsstelle in Munich. You see the reference point, also this red X vertically in the middle and horizontally laterally offset to the right. In this case, we don't have TL material inside. We have two ceramic detectors made of beryllium oxide, so it's OSL technique. Okay, how about the participants? The intercomparison was open to every calibration laboratory, as I already said, all over Europe. As you will see, we also had an institute which was from far away. Then as the reference lab, we chose the PTB in Braunschweig. They irradiated 10 dosimeters per quality, plus also 5 background dosimeters for a transfer dose and so on. Coordinating lab was KIT, and we were largely supported by Christian Renitsky at Cybersoft Laboratories. Thanks again, Christian. So, as you can see, we had 21 participants from 15 different countries, 20 in Europe, plus 1 participant in Japan. So, okay, here I show you some photos of the different irradiation setups. For example, these two ones, the one in the middle and the one in the right corner, are the setups at KIT. We chose to irradiate 4 present dosimeters at once, or 2 area dosimeters. Other participants, they only irradiated single personal dosimeters on the Phantom, as you can see. In this case, no build-up plates. Here you can see different setups with build-up plates, single area dosimeters hanging or standing on foam bricks. So there was a large variety of setups which you could see. Okay, then first of all, the background doses. Here you can see the different participants, and one of them had an increased transport dose, which wasn't too bad because we subtracted the transport dose from the measured dose of the irradiated detectors later on. So it wasn't too bad if something like this happened. But as you can see, there probably was an irradiation during transport. This is the same slide for the area dosimeters, which were irradiated with N60. You see the participant here with a high transport dose didn't take part in this type of irradiation, or didn't choose this category. Background dose for the personal dosimeters to be irradiated with cesium-137. Same thing here, of course, same participant, same irradiation during transport, and same thing here, personal and 60. Nothing special happening here. So the date of irradiation was also given by us. The irradiations were to be done during calendar week 45 in 2020, which was at the beginning of November, as you can see here. You see all of the participants, they did it at the right time. There was no issues during transport or so on, even far abroad to Japan. Next thing is how many of them used the PMA build-up plate, and as you can see, about 2/3 of the participants used the builder plate, the rest didn't use the plate. Okay, now the results. Just one thing, what we stated and issued in the certificates was the relative deviation, delta H relative, of the reported ambient dose equivalent, which is here called HIRR, from the measured ambient dose equivalent H measured, and was determined by the ratio of these two quantities. So, as you see, this irradiated dose was what the participants stated in their documentation, and as I said, the measured dose was the dose measured in Munich or in Karlsruhe. First, the measurement results of the area dosimeters irradiated with cesium-137. As you can see, there was one participant who irradiated, or let's say the measured value was 11.4 millisieverts, pretty high, because we demanded 10 millisieverts, which leads to a pretty large deviation, of course. As you can see here, participant T, they only had a measured dose of about 10.6 millisievert, but the reported dose was pretty low. It was, in this case, 9.1 millisievert. So, of course, the deviation is very large at this point. Next thing, personal dosimeters irradiated with cesium-137. As you can see here, there was also one laboratory with measurement results of about only 9.2 millisieverts. And as you can see, this leads to one of the largest deviations. Participant T, same thing here. Good measured, but the reported dose was way higher. Next thing, the area dosimeters irradiated with N60. As you can see, we had about 20 participants irradiating with cesium and or N60, and 10 which irradiated with N60. So here also a variety from 10.4, let's say, to 9.8. And the resulting deviation can be seen here, with more or less large uncertainties in this case. And the last ones, the personal dosimeters irradiated with N60, also about 10 pieces, and a variety from 9.4 to 10.4 millisieverts, which led to this deviation. So, but you can see, even though there's one or the other outliers, let's say nearly all of the participants, they had deviations between minus plus 10% of the demand value, which states that the calibration methods, at least which were performed in these institutes, they're very good, and they worked out pretty fine. So the thing is, we've planned to do another intercomparison after the mentioned IC 2021 area intercomparison. So probably in 2022, the next IC-CALM intercomparison is going to take place. Okay, that was it from my side. Thank you for your attentions. Now I think we have a few minutes left for questions. Maria, I'd say we start with the questions dealing with your presentation.
Yeah, some of the questions I've been directly answering in the chat, but we have some different questions also in different parts. So let me check the ones that have been answered. At present, there are not questions for you regarding your presentation, but as I'm going to answer the ones related to mine, maybe they appear in a few minutes. Okay. There is some interest about, for instance, why, if someone asks if it is common to use Hstar 10 as the operational quantity. I must say that Hstar 10 is the operational quantity that should be used for area monitoring. So this is the right situation stated in the different standards. And the same researcher asks about the use of Hstar 10 for beta radiation. of course, it depends on the situation and depending on the dose range that you try to monitor. Because, of course, for beta radiation of low energy, Hstar 10 maybe has no sense, and then it is necessary to use H'007. So it depends on the specific use of the dosimeter for the specific situation. As regards the same researchers asked about the corrections about the background and the transport corrections and the importance of these contributions. It depends on the monitoring period. For instance, if we are talking about a 1 year monitoring period, 1 day or 2 days or even 1 week of moving of the transport, just to send the dosimeters and going back is not too much. But if the monitoring period is 1 month, then we should watch, we should be aware about which is the days devoted to this transport. So maybe in that case, the contribution could be large. This is why it depends on the specific procedure. This is why it was important to say, okay, 3 months is the most frequent monitoring period. 3 months it's not very large. It's not 1 year, but at least it's not just 2 weeks or 1 month. So for 3 months, 1 week is not too much, but you should take into account, I mean. And regarding neutron dosimetry, there is not only interest in neutron dosimetry around nuclear facilities, regarding, I mean, the reactors. But of course, if you should keep in mind that we have synchrotron facilities. We have a lot of proton therapy facilities in Europe. So neutron dosimetry for workplace, for area dosimetry, it is coming more necessary when time goes by, because we have more and more facilities that means exposure to neutrons. So I think that this is important. I think that I've answered most of them. Let me check once again about if I forgot something. Anyway, someone asked me how to know more about Eurados. Just please visit our webpage, and if you identify some specific interest in different working groups, you can contact directly with the coordinator of the subgroup or to the secretary of the subgroup. So if you, for instance, if you are interested in the activities of working group 3, you can contact with Arturo or with myself, and then we can answer some questions about and disseminate information about when the annual assemblies are going to take part and so on. And another question about, let me check. Okay, yeah, Jean-Marc Bordy he always goes to the point. Of course, most of ambient environmental dosimeters on the outdoors, they are exposed to cosmic radiation, and of course, they are not calibrated to measure cosmic radiation. So, if you check our articles, papers about the results of the intercomparisons, you are going to see that the systems, when we look at the cosmic radiation, they have an over response to this radiation because they are not calibrated to measure that. As I've mentioned, they are usually calibrated using a cesium source, and this calibration factor is used to get the final dose. So, for instance, of course, there is a room of improvement on the algorithms to calculate doses in that cases. And I don't know, I think that maybe I think that I do not forgot anything. I didn't forget anything, but if there is any question, if not, we are on time. And if not, maybe we can just maybe, if you are there, Christian, you can turn on your camera just to say goodbye to all the audience. And let me say that it has been a pleasure to be with you today. I think it's very nice to know that there are a lot of people interested in this topic, and you sent very nice questions. and hope that at the end you will join to Eurodos or at least participate in this service on these intercomparisons. So that's all. Thank you very much for being here. And bye-bye. I hope that you have a very good afternoon ahead. So bye-bye.
Bye-bye.